All right, so this video gonna be on compressors and turbines. So if you're doing cycles, this is the video. Okay, so at my work, I do a lot of gas turbines. So I'm going to use a gas turbine as an example. So let's do this with some numbers. So let's say, all right, by the way, this is the symbol of a compressor. This is a symbol of a turbine. This is the combustor part, but we're not going to worry about that in this video. I already made a combustion video. So let's say we have ambient conditions. So pressure is 100 kPa, temperature is 300 Kelvin, which is 27 Celsius, which is actually kind of hot, but there are places where it is very hot. So I'm just going to go with it. It was a nice even number, so I picked it. Is that a bug? That might have been a bug on my computer. What the heck? What the heck? Okay, so typically compressors have a pressure ratio. Same with turbines, but yeah, they have a pressure ratio. So they compress as a factor of a number. So for example, this compressor, I just said it has a pressure ratio of 10. So that means P2 will be 1,000 kPa. It'll be 10 times 100, which is 1,000 kPa. Cool. Now, what's the temperature? Yeah. Start by writing down the equation that I said to write down in the entropy video. With that equation, we're first going to calculate the isentropic temperature, so assuming no entropy is generated, and then we're going to calculate the actual temperature and then see what our actual compressor efficiency is. 100% efficient compressor means you get to the isentropic temperature. So let's do that. So assuming isentropic, that goes to 0. We're dealing with pressures and temperatures, so we're going to use the second equation. Technically, compressor also compresses from a volume perspective, so you could use this equation, but I've never used it, so I'm gonna just stick with the pressure one. So the way you do this is you would say 0 equals, I'm just gonna write in the numbers, and I googled the numbers beforehand. CP is 1,000. It does not look like a 1. 1,000 times ln of T2 over 300 Kelvin. Use absolute units. Don't use Celsius, and don't use Fahrenheit. Use Kelvin or Rankine. Minus R, which is 0. What is it? No, in this case, it would just be 287. 287. Ln pressures P2 over P1, which is 1,000 over 100. I could have just done 10 because that's the pressure ratio. That's fine. Cool. And from this, we can solve for T2 equals, did it on my computer. It is 581 Kelvin. Cool. However, as I mentioned, this is the isentropic version. So to denote that, I'm going to write an S there. So T2S is 581 Kelvin. So what is the actual T2, or T2A? T2 actual. To do that, we have to use the compressor efficiency equation. Would you look at that? I remembered it by looking at my equation sheet. Okay. So a compressor's efficiency of compressor is isentropic work over the actual work. So the idea is the compressor wants to spend the least amount of energy possible to get your pressure up to P2. If it spends, and that's, so the least amount of energy possible is isentropic work. The actual work is going to be more than that, which is why it's on the bottom. So that's why this number will end up being less than 100%. Okay. The equation for these are MCP T2S minus T1 and MCP T2A minus T1. So MCP cancels out. You're just left with T2S minus T1 or T2A minus T1. Cool. So at a bare minimum, if our compressor is operating less than 100% efficient, that means that the actual compressor discharge temperature, or T2, is higher than T2S. Cool. And I guess that makes sense also, because the least amount of work, if you're saving work, that means less of your energy is going into temperature. So it makes sense that a less efficient compressor puts more energy into temperature, which no one cares about because it's a compressor. It's supposed to compress it, not heat it up. Okay, so let's finish off this example. Let's say that we have a compressor efficiency of 80%, so 0.8. So that would equal 581 minus 300 over T2A minus 300. T2A would equal, let me solve it on my computer, 0.8 equals I used to use Symbolab, but they changed it like sophomore, junior year of college to output fractions as fractions and not even solve your equation anymore. It doesn't output a number anymore. So now I'm using Mathway, and Mathway it's not as clean as Symbolab, which sucks, but it outputs numbers with decimals, which is great. All right, so T2A I got is 651 Kelvin, and good because it is higher than T2S. So that's a good check. So T2 actual is 651 Kelvin, assuming compressor was 80%, messing this up, 80% efficient. Cool. Now let's go with the turbine. I'm going to write the states down here. So let's say T3, what's a good turbine temperature? 1000 Kelvin. Let's go with that. That's a nice round number. P3 is the same as P2 because turbines are ideally constant pressure combustors. 1000 kPa. Cool. So how do you get state 4? Well, let's assume you're going back down to atmosphere. So the pressure ratio is, let's say it's 10 again. Well, it is 10. P4 be 1,000 over 10, which is 100 kPa. T4, and we have to do a very similar thing as with the compressor. So let's start by doing this equation again, very similar to how we did it right here. 0 equals 1,000 ln T4S. This should be T2S. T4S over T3 minus R ln P4 over P3. I think that's right. The 4 and the 3 might be swapped top and bottom, but let's see what this gives us. Oh, I didn't write out what R was, but that's fine. $5.16. If I swap them, no, it doesn't. It doesn't matter, because if it's swapped, effectively you could just bring out a negative in the front. So a negative, that would swap to a positive, and then you could move this whole thing to the other side, and then you'd go back to positive and negative. So it doesn't really matter which one's on the top and which one's on the bottom. Interesting. How exciting. Okay. So T4S equals 516 Kelvin. But what is T4A? So let's do the exact same equation. NT for turbine efficiency, let's say it also equals 80%. However, this time, instead of isentropic over actual, it is still isentropic over actual, at least it better be. Yeah, it is. And that equals, I'm gonna skip writing this part out and just cancel out the MCPs. You'll end up with T3 minus T4A over T3 minus T4S. Interesting. Let me double check that. I'm not going to restart the video. You just have to wait. Google says. Yep. 516 is right. Interesting. Oh, that makes sense. That makes sense. All right, let's finish this out and then I'll try to explain why I think it makes sense. So T3 is 1,000. Gonna get rid of the units, although you should always include the units. T4A over 1,000 minus 516. This equals 613. Okay. Cool. Cool. Well, I think it makes sense because a turbine's trying to extract. This is upside down, that's fine. Turbine's trying to extract as much energy as possible. So a compressor is trying to use the least amount of energy as possible, which is why isentropic's on the top. Turbine is trying to extract as much energy as possible, which is why isentropic's on the bottom. Because in a perfect world, you can extract all the energy. That's why isentropic is the baseline. That's why it's the max. Yeah. So if there's still leftover temperature that could be reduced down, you haven't extracted all of the isentropic work. Cool. Well, that is how you do a turbine. I'm just going to finish this problem off by calculating turbine efficiency and turbine power output. Except I don't have a mass flow rate for the turbine, so I'm not going to actually get a number for power output. But let's do efficiency first. And turbine would look too much like that. And GT for gas turbine. What would it be? It would be the power. I have it written down. I gotta go back to undergrad thermo, not grad thermo. I could figure it out if I thought about it. But let's see. W net over Qn, which makes sense. So Qn, you're adding Q. And how do you know how much Q you're adding? Because it is, okay, that makes sense. So what is each term here? So W net is the power produced by the turbine section minus the power consumed to compress the air. So the turbine is basically a big fan. So all of the combusted air spins the fan, and this fan it's connected through a shaft to the compressor, and it spins the compressor, which is a fan but faced the other way, so pushes the air. So basically, net is W turbine minus W comp over QN. QN. That's equals, not minus. All right, so what are each of these? These are MCP. Turbine would be T3 minus T4A. Yeah, that makes sense now, because if you're isentropic, T4A would be lower. It would be 500 instead of 600, which means W turbine is bigger. All right. So that's W turbine minus CP, W compressor, which is T1 minus T2. I want this whole number to be positive. So I want T2 minus T1. I want all these terms to be positive. That's going to be positive. That's going to be positive. Okay, we're good. Over Qn, which is a difference between 2 and 3, because Q goes into the combustor and heats you up from 2 to 3. So it would be MCP T3 minus T2. Cool. Q is effectively the fuel being inputted into the turbine. But yeah, okay. In this case, let's assume, okay, technically CP is not constant throughout this whole problem, because CP is a function of temperature, and our temperatures are ranging by a huge amount this whole problem. So the assumption that we have a constant CP is not a good assumption for this problem, but I'm assuming it is constant. So there you go. You get to cross out all the CPs. The mass flow rate. The mass flow rate of air entering the turbine is the same as it leaving. However, you're also adding mass flow rate of fuel with the Q. So technically, the mass flow rate through the turbine is slightly bigger than through the compressor, but the amount of fuel that you add is basically negligible to the mass flow rate of air, so you can also kind of assume that mass is constant. So you're left with just these. T3, 1000 minus 613 minus 651 minus 300 over 1000 minus 651. And you get a gas turbine efficiency of 10%. I think probably this 1000 Kelvin, was that too much or too little? What is 1000 Kelvin in Fahrenheit? Damn, that's like nothing. That 1000 Kelvin, I should have done like 1600 Kelvin. But again, this is just a practice problem, so it doesn't matter. I got gas turbine efficiency of 10%, 0.1. What is it, 0.103? Let's go. That's pretty freaking bad. Yeah. That's pretty freaking bad. But I think it's just a rule. If you increase T3, you get more efficient just by default. I think. I don't want to redo the math for that, but I think that's kind of right. And I think the reason why you can't go super high for T3 is because it literally melts the parts in the gas turbines. But yeah. So that's the efficiency of the gas turbine. Now the power output, work. So let's assume this gas turbine is connected to an electrical generator. So it spins the electrical generator. How much work would it produce? Well, it would produce the turbine work minus the compressor work, which would be MCP T3 minus T4A minus MCP T2 minus T2A minus T1. Unfortunately, you can't cancel out the masses, so you actually need to know what they are. But we know CP, we know the temperatures, so if we knew the mass flow rate, we could get the number, or we could get the power output. Or if you're given the power output, you could back calculate the mass flow rate here. That is literally it though. That is all of compressor and turbine stuff in thermo. Cool beans.